Welcome, everybody. I'm excited to be doing this presentation. The conference has been outstanding. Every speaker has done a great job, and the information they presented has been informative and useful. I've been taking lots of notes and looking forward to following up on that. This particular presentation is titled Proof of Concept of an All-Sky Antenna for Use in a Synthetic Very Long Baseline Array and Lessons Learned, and I put a lot of lessons here. And this is a follow-up to a presentation I did 2 years ago at the Owens Valley Observatory, where I talked about a long baseline interferometer that I wanted to do for that I proposed to do for amateurs. And so if you want to know more details about that, you can go back and see the presentation that SARA's made available. But this will be just a follow-up on that, and I'll talk a little bit more about that here in a bit. Also, this presentation is intended also to be directed at people that are somewhat new in the hobby, and this is a result of conversations I've had. I'm a member of the San Diego Astronomy Association, and we've recently started a special interest radio astronomy group. And in the course of that, we have discovered there's a lot of people who are very experienced astronomers optically, but not radio. And so the topic of of how you actually do radio astronomy is somewhat new to them. And as I've discussed this with them, the questions of sort of how do you do it and how do you know when you actually see something has come up. Also, the very simple fact of how do you do radio stuff has turned out to be a little bit of an obstacle. So I'm going to talk about that in this as I explain my experience here. And also, as I was talking with Ken Redcap and others that were preparing this presentation, the notion of how does ChatGPT, and that's the artificial intelligence app, I guess, that you can go ask questions. How can that be useful? And so we talked about how it could be useful in doing radio astronomy, including doing maybe some analysis. So I've deliberately put some of that in here. And when that happens, I'll share it with you so that you can see, and then you can have a little bit of exposure to it and decide for yourself whether it's a useful thing for you. So I'm going to start with, we're going to follow just a little bit on Jason's presentation yesterday, where he talked about the great work that he's doing with the Green Bank 20 meter. And we mentioned while we were having a discussion about that as he was presenting, that there were some images and I wanted to just present some of that so you can see what the capability of that system is. It's a highly underused resource for us, and I wanted to just let everyone see what it is in the hopes that maybe that could be some useful information. Now we're going to take just very, very, very brief talk about arrays and interferometers. And as I said, if you want more on that, plenty of people have done great presentations, and you can get lots of YouTube videos. And some of that's also covered in my talk in that Owens Valley 2 years ago. So we'll talk about that. Then I'll just briefly remind us what the proposed very long baseline interferometer that I'm talking about doing is, and the proof of concept of that, which was the experimental basis for this presentation. And then I'm going to talk about how do you know if you're actually successful at finding something. Can you see the sun? And as I said, it'll be some data analysis. And as I said, we'll talk about some ChatGPT stuff as well. So let's see, there we go. So this is actual images produced by the software program that controls the Green Bank 20 meter telescope. And in particular, this is, so last year when we were at the Western Conference down in Texas, so it was total eclipse there. In West Virginia, where the 20 meter is, it was not a total eclipse. And the way you read this image here is you start down in the lower left, and as time goes on, you go up the left side, across and down. And as you can see, actually it's the other way around. Sun starts here bright, goes down and over to the right and back up. So what's interesting about this is it wasn't a total eclipse in West Virginia, and you can see this. So as the eclipse started, you see it takes more and more of the sun, but not all. And so, like I say, what's interesting about this is not only was the data taken here, but it produced these images. And you can go back and look at work that other people have done. So I didn't take this particular image, somebody else did, but you can, there's a search tool there. You can go back and look, and you're able to look at things like eclipses or like M101 or whatever. You can look what other people have done besides yourself. So this is Cassiopeia A, which is supernova remnant. It's one of the brightest radio objects in the sky at particularly at lower frequencies, lower meaning less than the hydrogen alpha line. And as you can see, it's a beautiful picture here. This is actually the scanning path that the 20 meter takes when I looked at this. And the way you read this is down in the lower right hand corner, the little round, the green circle here. This is the beam width, and I set it to do a scan pattern, and it goes back and forth and back and forth and back and forth, and in much bigger than the object that we're looking at. And as Jason talked about yesterday, you can get the spectral components of that, and sure enough, there it is. And I won't talk more about that now, but this is the actual image that I did, and about a year ago, using that 20 meter to look at Cassiopeia A. And so, as you can see on the right hand side, this is the scale. So it's hotter in the red and lighter in the blue. So there's the actual image. And now to compare that, the one on the right is the ones the professionals did using the very large array. And I think they did that in about 5 or 6 hours, and tremendous detail with obviously all the resources of the very large array. The one on the left is the one I did using the 20 meter in just a few seconds. And obviously I don't have the detail of the professionals, but as you can see, mine actually looks quite a bit like the professionals do. And this is a tremendous thing. So let's go one step further. If you take the data, you can produce a sky map, and I'm going to talk a little bit more about this later. But here's my sky map, and that I actually produced, made myself. And the bright object that's right here at about 12 o'clock, that's Cassiopeia A, using my other radio data. So I just wanted to see kind of what does my data look like compared to the pros. And obviously the pros are way better, but using the 20 meter, which is a tremendous thing, you can get these kinds of images like you can see here on the left. So it also occurred to me, what happens if you look at an objects that don't produce much radio? So this is an optical picture of M56, which is globular cluster, and it's beautiful. And then here's the spectral analysis of it using and by the way, this is all software that's built into the 20 meter, does all this for you, as Jason pointed out. But this is the image that you get, and notice it doesn't look anything like the very crisp image I got for Cassiopeia A. Why is that? Because even though it produces a lot of optical light, it doesn't produce very much radio, so you don't get a very defined radio image. And so I just wanted to show you that as an example of how optical and radio sort of work together to show the different parts of the spectrum, which help you understand what's going on in the universe. Now, after Jason presented yesterday, Jackie, who's here at the conference, asked me, well, they must be using, us, we amateurs, we must be using that telescope, the 20 meter, all the time. It must be, there must be no time to get it. And it turns out that we're not. Now, obviously, we share that. It's actually being run by University of North Carolina, and we have minutes allocated to that. But it's usual that we have plenty of minutes left over. So if people wanted to use this, it's a tremendous resource that's not well understood or not well known about within the radio astronomy community. And you could really do a lot with it. Also, if you're looking for actual science projects that you want to do with this, you could do that. Go to University of North Carolina's radio astronomy page, and they will tell you about projects. They can suggest projects, I guess what I'm trying to say. So anyway, that's that. And I just wanted to be able to put that on there so that the group can be aware of what possibilities there are. So now switching right back into my presentation fully, the in Craig's talk yesterday, he did a great job of introducing the notion of what arrays are. And the only thing I just want to hit just a couple of high points here. I'll leave the material in here for the slides for the so that when it comes out in the publication, you see it. But I'm just going to hit a couple high points. And one of the high points is there's kind of two types of arrays. There's phased array, and as Craig was reminding us, that's where you actually take the antenna, and by using beamforming, you actually point it at a certain place in the sky, and you take the data, and that's phased array. The other kind is sort of a synthetic capture, and what you do there is every antenna takes data, and then all that data comes together, and you could either in real time by using time delays, as I'll explain in just a minute, you can aim it, or you can do it in post-processing. But when you're using the synthetic aperture, you're not aiming the telescope at a particular point in the sky. And let me just talk a little bit more about that. So what a synthetic aperture array does is so the synthetic part is it mimics a much larger telescope. And so what's the large telescope? It's if you have a whole bunch of antennas, the longest distance between any two of them is what determines the resolution of the antenna array. And so even though these antennas may be either closely packed like they are down here in the bottom, or far apart sparsely as they're done in the top, you still get the antenna or the effective antenna as being the combination of all the antennas together. And it's the distance between the largest two is what the antenna acts like it has the resolution of. So that's the key idea here. As I said, the data is collected from each antenna, and then it's correlated. So what's correlation? And when I did the presentation 2 years ago at Owen Valley, I even had a slide that had a correlation, and I put a little ghost on there because it's scary. But what correlation, if you think about what it really means, is what's the relationship between two different signals? And so what I'm trying to show is the relationship between the signal received on one antenna and another. And correlation allows me to be able to put those two together and see what that relationship is. And so the very large array is a synthetic aperture antenna, or sorry, synthetic aperture array. And there's 27 of these 25-meter antennas, and they're out on these three Y-shaped arms that are 13 miles long. Now, when the antennas on the very large array are out at their furthest point, which is the A configuration, the resulting antenna here, the longest distance between two antennas across there is 36 kilometers, about 22 miles. So even though each antenna is only 25 meters in diameter, the effective antenna, because of their spacing, is as though you had a 22-mile in diameter telescope. So let's just briefly talk about interferometry. So interferometry is that what happens when one wavefront hits an antenna before another. And let me do a little picture here. So most of us maybe have seen this picture before, but electromagnetic radiation comes out in space, and of course it comes out as a sphere, but as it expands across space, the sphere becomes so big that the front of that, basically the wave, so in other words, the same place on the wave, is basically flat. So we call those plane waves. And so as you can see in the demonstration here, as the plane wave comes down and at some point it's going to hit antenna one. And then if you just do the geometry, you'll see that it takes some time to go down here what I've labeled A to hit antenna two. And that's a delay. So the exact same signal that hit one hits that at time zero. And then at time zero plus whatever the time it takes to A hits time two. So whatever the time it takes to go that distance is unique for where in space that is. So if you could imagine that instead of coming off here to the upper right, like I've done it, maybe it's a little bit more to the top. Well, that distance would be less, and so the time delay would be less. So the time delay is exactly related to where exactly and uniquely related to where in space that the electromagnetic radiation originally came from. And you can figure that it's that time delay is a function of the distance between the two antennas, the angle it is up in space, where it came from. So the baseline and where it came from, the angle here. So like I said, if you want to know way more about that, there's plenty of YouTube videos and other presentations or plenty of books that you can go read that. So I just wanted to briefly talk about that here. So the effect of that is if my antenna would have a beam width, I'm showing here in the north-south direction quite big, by using interferometry, I can bring, and I just have one axis, so along an east and west, I can take that dimension, instead of being all of this big, huge one, I can make it very, very narrow indeed. And if I expand that to two dimensions, meaning I have antennas not just, for example, along the east-west axis, but I include north-south. So in other words, there's X and Y. Then I can get even more resolution and narrow that down in let me show you the picture, so that it's much smaller in all the dimensions. So now the other thing about this is that even though maybe it's the signal of interest that I'm looking for, so that's going to hit this antenna first and this antenna and so on and so forth, there's going to be unique delays in the timing it takes to hit these antennas, depending on where that, in this case, the red plane waves are coming from. Well, there's also going to be a different set of unique timing delays for hitting these antennas if it comes from the green direction or the blue direction. So the antenna is receiving all of these signals superposed upon each other. And so part of our challenge is to how to be able to pick out of there which one is the red signal versus the green or the blue, for example. Also notice that even though this is signal of interest here, it's also picking up noise, some of which comes from space and some of which comes from your neighbor firing up his 55 Chevy with the unshielded ignition. So all of these sources of electromagnetic radiation are going to be picked up by these antennas. And so part of the trick here is how to pull that out of there. And as I said, you end up with a very narrow, very highly resolved field of view for the antenna. Okay, the very large array has 27 antennas, and I think I calculated if you look at each one acts as a pair, and then you take each pair's data and you correlate that with all the others. This picture here on the right shows the very large array. I actually drew all possible combinations, and as I recall, it's 350 or something like that combinations here that the correlator has to be able to do. The good news about the correlators are they used to do them with hardware. Now they do it with software, and much of that software is available, so you don't have to write your own correlation programs. Just one more thing about this, that resolution, the size of the angle field of view you get in space. This is the equation, and D is the distance between the antennas. So as that goes up, the field of view goes down, which is good, makes it smaller in the sky. Also, as your wavelength goes up, your field, I'm sorry, as your wavelength goes down, the field of views goes down. So higher frequency stuff also produces smaller field of views. So now switching now to just what ChatGPT can do. So I decided to just try ChatGPT and say, what is very long baseline interferometry? And here's what it came back with. It's a radio astronomy technique, and it basically goes on for pages. Here's how it works. It gives you all the details of that. And why is it so powerful? I didn't even ask that. It just suggested it. And unmatched angular resolution. And most people don't realize that radio astronomy gives you even better resolution than the James Webb. And so here, no atmospheric limitation and so on and so forth. It suggested on its own applications of very long baseline interferometry, and then gave some famous very long baseline interferometry networks, including the very long baseline array, which I'll talk just briefly about. So I use ChatGPT pretty much every day in my work, and here's what you learn from that. It's good. It's a good helper. Um, don't rely on it entirely, but it's better than starting with a blank sheet of paper. And it gives you good information. It's a good start. And I think the same is good for this kind of thing. One of the things that worried me initially about this was um, when I first started playing with it, I thought there were no sources. But if you look carefully when you do ChatGPT, down in the bottom of it, there's always something that says sources. And if you click on that, there actually are sources. So you're not just taking somebody's word for it just because it came from the internet. It actually has the source material that it used, and which is useful. So the very long baseline array is 10 antennas. That was one of the very long baseline interferometry things. And it stretches from Mauna Kea over here on the left, clear over to the St. Croix and the Virgin Islands, with 8 other telescopes at various places, including Pie Town, New Mexico, which is 30 miles down the road from the very large array, and other places, including Iowa. I mean, didn't even know New Hampshire. We saw the one that when we went to Owens Valley 2 years ago. We saw theirs up there. But so here's the array. And as you can see, it has a very long baseline, about 5,000 miles. And interestingly, it gathers so much data that they put it onto hard drives, and they physically bring them to the National Radio Observatories, the Pete Diamantini, I guess, Science Center there in Socorro, where we're having this conference. And anyway, so what my proposed idea is when they do each one of these antennas, these are not physically hooked together. I mean, it'd be almost impossible to do that. So what they do is they record data off here with so what they record is a very precise timestamp and the data. So in other words, what is the data? It's what they're reading for a voltage on the pickup on the antenna. So maybe it's 0.1 millivolt or 5 volts or whatever it is, and versus a very precise timestamp. And then they bring all these collections of timestamps and data back to the center here in Socorro, New Mexico, and then recombine them in a way that produces the image. So what I was proposing to do as an amateur is we have amateur telescope arrays around, and we do the same thing, record the data, and then somehow it gets back to a central location, and then we can process it to produce the images. And in particular, the science that I wanted to do was I wanted to be able to look at time varying things such as pulsars within the time that you're taking data. So in other words, if you were taking data for an hour, you would look at things that vary in that time scale of an hour. And then the idea was to do this over time. So maybe you take data every month, and you'd see things like, so Cassiopeia is a supernova remnant that's expanding. And so month to month, you'd be able to see that expansion. And so I wanted to be able to look at time varying things over both the short time scale, you're actually taking data, and then compare it from data taking session to data taking session. And as I said, if you want to know more about that, you can see the presentation I did 2 years ago. So I want to be able to do a proof of concept of that. And my question was, so what I want to do that's slightly different here, among other things that's slightly different, is normally when you take an antenna, you aim it at a particular thing. And normally you want the antenna to be very small field of view. So you're looking at the object you are and nothing else. And then often when you do that, you also get the benefit of being able to have gain. What I was proposing here instead is that you have an antenna that looks at the whole sky at once. And then by taking all these whole sky surveys from all over the place using interferometry, and then using those time delays that I was talking about, you're able to then virtually aim the antenna after the fact, so post-processing, and be able to aim it in the sky. And so in order to make that work, you would have to, I wanted to see how easy that would be to do. So my idea was to take a single small wide field, in other words, wide field of view in the sky, antenna, and hook it up to a radio and see if I could see anything. And so because I wanted this to be a little bit scientific, I did a scientific hypothesis. And I said, I want to say, could I see the sun? Because the sun is a bright radio source. Or also maybe the Milky Way as it passes over. So I hypothesized I would be able to see the sun with the horizontal loop and a double bow tie antenna. And I'll show you what these are in a minute, but not with a disc cone antenna. And so I'm going to talk about my results that I came up with when I did that. So first off, the frequency I was looking at here is I used 150 megahertz. And so why? Most of us in SARA look at the hydrogen alpha line, so 1428 megahertz. And I'll have to tell you, I've never looked at that on. I suppose I've been around long enough in radio astronomy how to do it. But most of my observing has been at about 611 megahertz, 611 megahertz. And I'll talk a little bit more about that. Some up at 12.2 to 12.7 gigahertz. And but what one of the things that's intriguing about 150 megahertz is when you're not looking at atomic transitions like you are at the hydrogen alpha line, you're just looking at thermal radiation or bremsstrahlung radiation or synchrotron radiation. If you're looking at all that, so the electronic transitions, the things you're looking at are much brighter at lower frequencies, as what this chart shows here. So as you go up in frequency, the galaxy towards the pole, Cassiopeia, Cygnus A, those things, those go down in strength. And so if you go lower frequencies, they're brighter. And so that's good news. The bad news is as you go to longer and longer wavelengths, the antennas tend to have to be bigger. So that's the sort of trade-off. But I thought, well, it'd be interesting to see what's happening down here at 150 megahertz. And so when you set up any kind of a radio telescope, a total power telescope, you need to have an antenna. And here's a picture of the horizontal loop antenna. And just, and I'll have another slide here in a minute, but so you have an antenna. This is for newbies, you absolutely have to have a low noise amplifier almost immediately right where the pickup is on the antenna. The reason for that is these signals are so weak that they will not make it through the coax cable. They will literally get absorbed. So it's a little saying in radio astronomy that a strong radio astronomy signal is a cell phone on the moon. And I didn't believe that, but using my physics background, I calculated it one day, and sure enough, that's true. So the fact that I can pick up a cell phone on the moon in my noisy backyard in the suburb of San Diego is pretty impressive. But still, that's a weak signal. And if you do not put a low noise amplifier right there on it, as you can see, here's the antenna, and literally right as quick as I can get it, here's the low noise amplifier to be able to preserve the signal and to be able to send it down the coax. Then you send it down to some kind of a radio. So what I did for this is I used a dongle. So this is the FunCube Dongle Pro, which I have. And then you hook that up, you just plug it in the USB port of a computer. And then I used SDR console software. Now, in talking with other people here, I probably should do SDR sharp, but in point of fact, I use SDR console. And then you have to hook it up to some way to sort of record your signal. So I use the Radio SkyPipe software, and I've used it for years, and I really like it. There's some other cool stuff out there, and including some of these software packages, software-defined radio packages that allow you to record. But this is the setup that I used. So here's once again the three antennas, and you can see here's the horizontal loop, and so it's basically what it is it's one wavelength all the way around it. So what's the wavelength for 150 megahertz? So the trick is, remember, you take 300 megahertz and divide by your frequency, and that's your wavelength. So 350 divided by, or I'm sorry, 300 divided by 150 is 2 meters. So all the way around here is 2 meters for one wavelength around here. And then I also use my bow tie, and this is double bow tie, and this is one I've used for my 611 megahertz radio. And here it is. And then over here on the right is just MFJ 1868 discone antenna. So here's what the radiation pattern looks like for these. And remember, I'm saying I'm trying to get as much of the sky as I possibly can. And here's how you read these radiation things. So north for 6 o'clock to 12 o'clock, that's looking straight up. And 9 o'clock to 3 o'clock is the horizon. So if you look at the blue pattern here, from about 45 degrees to 45 degrees, it's pretty flat, meaning that the radiation pattern that it's receiving here is pretty good all across that whole way. And remember, 45 to 45 is in the whole circle. So that's 90, but that's really 180 degrees of the visible sky. So I'm basically picking up with this antenna 180 degrees of the visible sky. Now contrast that to the Radio Shack antenna here. It has about a 30-degree beam width. So that's half beam power, they call that side to side. And notice it's not flat, it's very directional in the direction that it's pointed. And then finally, look at the radiation pattern for the disc cone. Remember, this is straight up, or the 6 to 12 straight up. Notice there's nothing. So the disc cone is terrible at looking straight up, but look at it's pretty good side to side. And so that's because it's more of a communication antenna. That's why I said, I hypothesized that I'd be able to see something with these two antennas, but not with the disc cone. And by the way, what is directly overhead in Chula Vista? Well, we're at 32 degrees latitude. So what's right overhead at us is 32 degrees declination. So point my hand straight up, that's 32 degrees of declination when I'm in Chula Vista. Okay, so here I'm going to actually do this, and this is the lessons learned. So not only am I doing a new antenna, but I'm deciding to use a new radio. So the new radio is the software-defined radio. And historically, I've used an icon, and I've struggled a little bit with software-defined, but I decided to give it a try here. So I'm going to suggest, here's the first lesson. Make sure your radio works. And so when I decided to try this, I got the software-defined radio, and I hooked it up, and I played around. And so I got to the point where I could easily pick up radio stations, whether they're broadcast FM or ham radio or whatever. And so I thought, aha, I know what I'm doing here, and I got it to work. So hooray, I'll just plug it in. Now, as I said, I typically use an ICOM radio. and and I'll show you in just a minute. But I lucked out with my first radio telescope, and it worked well as soon as I put it together, and that did not happen this time. Um, so then, by the way, how do we know that it's actually working? And I'm going to show you this. You do some calibration, you check day to day, compare the data day to day to make sure it's correlating. You compare the bumps, the peaks and troughs to actual things in the sky, and maybe you can do a fast Fourier transform. So here's my the 611 megahertz telescope, and this was an idea that Shad Nygren presented at a Western conference at Stanford. So at the end of the meeting, we had some time, so he got up and said, "Why are we building everything ourselves? The UHF industry has spent a fortune on developing antennas and low noise amplifiers. Why don't we do that?" And he even suggested this Radio Shack double bow tie antenna. And I had been struggling with project to build to get my toe in the door. And this is like the light went off. And so this is what I did. So I took the double bow tie antenna, hooked it up to the Channel Master low noise amplifier. This is the ICOM 7000. This is a workhorse in radio astronomy, has been for many years. It's just a receiver, but it's a very, very good one. And then I take the output of that, and the output is just the audio signal. So a loud radio astronomy signal in a total power telescope is a loud hiss, and a weak one is a low hiss. I just hook it into the computer, use the computer's built-in A to D converter, and then produce the data. Now I do drift scan, which means I point the telescope either north or south at a particular declination, and I just let the Earth rotation aim the telescope. And I typically take data when I do drift scan about once every minute. And this image that you see over on the left is an actual data. So when I first started, I didn't know what an actual data signal looks like. That's what one looks like. Okay, and then this is in my backyard when you can see I was taking data there. And there's the ICOM. Okay, so one of the first lessons that you need to do is you need to clean up your data by averaging. So this picture on the top is what raw data looks like, and this is pretty noisy. You can see there's a signal here, but you can also see what the bumps here, that there's a lot of noise. And the noise mostly is going to be from stuff environmentally around, but not necessarily. And so down here in the left-hand corner is if I take every 3 data points and sample it, that cleans it up a little bit. But if I go 10, it cleans it up more. So you got to kind of figure out what produces the clean signal that you want. And that depends on how often you take data and that sort of thing. But look at the big difference between this noisy signal and the much cleaner signal down on the right. And it's going to have some consequences for evaluating the data, as I'll show you in just a minute. Okay, so here's the disc cone data. On the left is the raw data, and like I defy you to show me anything in that. And when I clean it up, even with the 10-point averaging, you can see it cleaned up this side quite a bit. But for whatever reason, there's still some super noisy stuff going on over here. And I was trying to figure out what that is. So I thought, well, maybe it had to do with time of day. So I figured out when the sun was up. And so here's when the sun comes up, and then over here's when it sets. And it doesn't look like there's any correlation between sunrise. So I don't know what's causing this. And by the way, though, this happens pretty much every day. And so whatever it is that's causing this is something every day, but I don't think it's astronomical. I think it's uh, local noise. And remember also that the disc cone doesn't see straight up anyway. So, and when you're doing radio sky pipe, it's easy. You can take the data and then you can output it. You can either view it smooth by averaging, or you can smooth it and then output it. So it's very easy. Excel also has ways of doing averaging. So how do you prove that it works? So this is the first light for my 611 telescope. And so I hooked it up, and sure enough, I was getting a signal. And how did I even know that the signal meant anything? So I aimed the telescope at clear sky. So what does clear sky mean? This is where the radio sky is not very bright. And so, for example, up around the North Star, it's not very bright. So I aimed it up around the North Star, and you can see here it is flat. And then I aimed it at the ground, and the ground is hot. And so you can see the signal went up. So I'm like, oh, okay, that's good. And then I stood in front of it, and I'm hot. And so you can see here I am, this is me. And then I stood off to the side, then I jumped in front again, here it is. And then, oh, well, okay. And then I disconnected the antenna from the system. And this is just the system noise in the ICOM receiver. And then I hooked it back in, then I hooked it back out. So when you see this kind of stuff, that gives you a pretty good idea that it's working. And you get what you expect to see. I expected to see some signal looking up in the sky. When I ground and me made it hot. When I took it out, it's not. Now, the next thing I did, and this happened to be with my 12.2 to 12.7 gigahertz telescope, I aimed it up in the sky and I was getting satellite stuff. So I just let it drift across there. And you can see here's a satellite, here's a satellite, here's a satellite. And I was trying to get the sun. And so I managed to aim it, and you could see the sun's transit back across there. And then after the sun transit, here's the satellite background again. And then here we are down. I stood in front of it, it goes up the same thing as it before. So here's two different telescopes sort of confirming that they're working. So this gives you an idea that your telescope is actually doing something, and of course you can do it again here. But what if you aren't seeing anything? So I remember I took that disc cone stuff and I looked to see, I put it on there and I said, where is things that should be producing radio signals? So for example, here, the two red lines up and down are when the Milky Way transited across there. And you see this high signal here, and it's down, there's really nothing here. And then Cassiopeia is very bright, and I showed where that is. Maybe that's there, but it doesn't really look anything. Cygnus A, which is another bright one here. Here's during the day. You can see maybe doesn't look like much correlation here, or Taurus A. So to me, it doesn't look like anything was matching up. And so, like, what is going on here? And so here's another lesson. Remember, this is the first time I was using software-defined radio to get this. So over here on the left is you can turn up the gain. And this is the default gain that it comes with. And so as you can see, default gain comes to 44 dB. And so I thought, well, these are weak signals. I had to crank it up as much as I can. So I cranked it up from the sort of default 44 up to 98. And I thought, well, if a little is good, a lot will be way better. And so anyway, for 2 months, I was taking data with the radio telescope at full maximum gain. And I was getting crap data like this. And so once again, using ChatGPT, I went to ChatGPT and I thought, well, let's see what it says. So I said, when taking radio astronomy data with a SDR receiver, is it possible to use too much gain? And boom, it comes back with, yes, you're an idiot, and here's all the reasons why. And then it suggested on its own how to optimize it. Well, start with moderate gain, and well, duh, now I know. And here's their conclusion. So anyway, it's kind of useful to see that. So so now remember why, when I'm cranking it all up, not only is it amplifying the signal of interest, but it's also including everything else, the local noise and crap and everything else. So I'm probably losing my signal in the way over amplified other stuff. And so, so just as a point here, would it help to take to integrate? So in other words, day after day and stack them on top. And so, yes, that'll absolutely work for removing intermittent noise like my neighbor's unshielded 55 Chevy, because he's not doing that all the time. He's only doing that occasionally. So absolutely remove that. And maybe for Poisson noise. So what's Poisson noise? Poisson noise is basically noise that appears because even though the signal is continuous, we're taking it in discrete pieces. And so some of the techniques to remove that kind of noise, it would help, but it absolutely will not help for system noise. So in other words, if I have a lot of a constantly running refrigerator right next to my antenna that's motors producing noise, it's always going to be there. And so taking it every day is not going to be able to pull my signal out of that. It's just going to stack on top of it that noise as well. So that's why it's important, if you can, to take your signal and move it away from sources of electromagnetic radiation like refrigerators or whatever else. So when I retake the data, and this happened to be, remember I took it for many months, including with horizontal data. When I take it with the lower gain, so on the left is with the high gain, and with the right is with the medium gain. And notice they don't look the same, but as I'm going to point out, the medium gain data is much, much better. And so now this is the horizontal. I will tell you, if I were to show you the high gain for the loop, you wouldn't be able to see anything much like the disc cone. But here's the horizontal loop antenna with the medium gain. And now look, so here yellow once again is the daytime, and the red is Milky Way. Well, look at that. When the Milky Way comes across, you see up comes the signal, and then it goes down when the Milky Way transitions across. And here's Cassiopeia A, and look, right where I expect to see Cassiopeia A, I see a peak. And here's Cygnus A, right where I expect to see Cygnus A, there's a peak. And so now it at least looks plausible. Things are sort of matching up, whereas they didn't match up before. And I compared, when I went to Medium, I compared my software-defined radio to ICOM, and we'll talk about correlation here in a minute, but the data is actually pretty correlated. And so that gave me confidence that my software-defined radio was giving me the same kind of results as I would be getting with my ICOM. Okay, so second lesson, correlation is your friend. And so remember, correlation means if you have a good positive correlation, as one signal goes up, the other goes up, and as the other goes down, it goes down. So, and just as a note here, if you have a 0 correlation, that means there's no correlation. If I have a 1 correlation, that means they're perfectly correlated. And then in between, of course, is weak, moderate, and strong. And so here's an actual piece of data from 2014. And here's this weird looking signal with fuzz on it. And so this is real data. So is there anything going on here? By the way, this is several days worth of data. It's a 45-degree declination. And you notice the signal looks mostly the same, but there's a little variance. You can see here's a little bump, something went on there, and something went on there. But notice that generally speaking, they start here, they go down, they go up, and they go back down. So I'm going to suggest that these signals are pretty correlated. Here's the same version in XL, and you can do it either. This happened to be Radio Sky Pipe, this happened to be XL. But so here's the actual correlation data for some 2013 data. So this particular data, and the way that you read this is you take the first day here, and then you compare it to a day here. Well, look at these correlations. These correspond to these actual data. The October 5th to October 6th, 0.95. Remember, 1 is perfect. 0.93, 0.89, 0.96, and so on and so forth. All this data is strongly correlated. So when you see data that's strongly correlated, that's a pretty good clue that you're actually looking at something, that the something, whatever it is happening regularly to every one of them when you do it, when you expect to see them. So this is a pretty powerful analytical tool to show that you're seeing something. If you had, so here's my correlation data for the horizontal when it was the super high. Notice, look at these correlation values. Remember, 0 is no correlation. And here's essentially 0. And by the way, you can have negative correlation, meaning as one signal goes up, the other goes down. But look at all these. They're almost no correlation whatsoever. And then weirdly, here's a correlation between February 11th and February 12th. And this is what that signal looks like. So who knows what was going on these days, and who knows, all of a sudden it's working here. But I guarantee there's nothing going on here on February, compared to February 9th. And here, look at the signals and you can see. Now, this is the raw data. As I told you before, look at how rough they are. When you go to 10-point averaging, it'll affect your correlation. But once again, even doing averaging here didn't help. And then when I did the bow tie, I got some sporadic, moderate correlation, but not great. You can see zeros and 0.56s all mixed in. And once again, here's other stuff. So what's going on? It's important to remember that correlation doesn't mean causation. So there could be something, it could be correlated, but it may have nothing to do with your radio signal of interest. But at least it gives you hope that something at least is going on, and it isn't just complete random noise. Okay, another lesson here. Remember that radio astronomy data is sidereal, meaning that it's not a solar day. So it's 4 minutes less. A sidereal day is 4 minutes less than a solar day. And you have to keep track of this, because if you take data over time, the signal of interest that you're looking at is slipping in time, basically. And so you have to make sure you're looking at the same data every time. And when you do radio SkyPipe, it's pretty easy. You can load that data as sidereal file. Now, once you've got your data, you need to match it up against the bumps in the radio thing. So here just happens to be sources. Here's where the objects are in the sky. Over here's their brightness. And so what I'm going to do is I'm going to look for strong signals where these things are. And you saw me already do that back up there when I showed you the horizontal loop antenna. And so, but you end up with kind of what I call a squiggly line problem. And the squiggly line problem is this is real cool. When I first started doing this, I'd show my wife and I'd say, boy, look at this. Look here, here's Cassiopeia or whatever. And she go, it looks like a squiggly line. And I go, yeah, but look, there's a bump. And she wouldn't get it. So I realized I had to kind of turn it into a picture. So just looking at the squiggly line here, as I showed you before, nothing matches up. So I'm going to posit that this is crap. And remember, this was also the high gain disc cone, or horizontal loop in this case. So there's nothing. Where Cassiopeia is, I don't really see anything. Where Cygnus A it is, where Milky Way, I don't see anything. But you can actually make an image. And so several years ago at one of the conferences, I talked about how I took different drift scans and turned that into an image. And this is part of that talk. And the first time I did that, I put it into Excel, and I just did Excel's 3-color thing. And so each one of these rows, it stands for a different declination. Here's 45 degrees, 55, 65, and 75. And you can see there was variation in there. And as soon as I saw that, I went, what if instead of using 3-color, I use 10-color, and then the really bright is purple, this indigo, and the really cold is red. And could I do that? And remember that signal I showed you that was just a fuzzy line, I called it? That's this. And yet out of that fuzzy line, I get this level of detail. And then when you take Stellarium lets you take their sky map, and I, by hand, posted these colors on here, and you can see, sure enough, where Cassiopeia A is, it's bright, and Cygnus A over here as well, and where up here towards where there's not much going on, it's cooler. And so, and by the way, I was at a conference at Stanford where I presented this, and a guy came up, I did this all by hand, and I suggested guys that were good programmers could turn this into a programming much easier, and he volunteered to do it, and I didn't take his name down, and I couldn't remember him. So anyway, those of you who are good programmers could do this. If you're looking for a good signal processing algorithm that preserves the highs and lows, early in my career, I guess I still am a patent attorney, I wrote this patent application for this, and this is an algorithm for taking data signals for ECGs, and this is actually one that's in probably the one that's the most used in the whole world. So this is an actual algorithm that's actually in use, and I'm just suggesting it. So now to close out with, I talked about fast Fourier transform, and what that is it's looking for components of the signal that are in time. And so I wanted to see what ChatGPT would do. So I took the disk cone data. Remember, I didn't think there was much going on there. And I just took it and I put it in ChatGPT and said, please analyze the attached file to see what the fast Fourier transform components are. And then I explained what the columns are and what the time was and so on. And it came back with, it doesn't look like the data, it's not automatically parsed into the column headings correctly. So in other words, it didn't like the way I put the data in. It wasn't the data itself, how I presented it. So it said, I'll clean it up. And here's what it came back with. It cleaned up. So basically it just put the date and then and the local sidereal time. And then here's the data for them. So I said, okay, that's fine. And then it came back and said, your analysis is complete and the frequency components have been visualized. And I'm just reading here. The plot shows the magnitude of different frequency components, allowing us to identify dominant frequencies in the data. And then, so initially it came back, and here it is. All the frequency components is clear down here in the 0 period. And so I'm like, what is that? Well, duh, the signal's sitting up on top of a huge voltage. And so when you look at it that way, that's the DC component. So I said, okay, remove the DC component and look at the data again. And this is what it came back with. And to my surprise a little bit, right here, this is the 24-hour period. So remember I said the data kind of looked the same. So something is going on there with that data, and it was able to pick it out here. Now, what these other big spikes are, I don't know, but clearly there's something here. So the fact that ChatGPT could do this was actually pretty cool. I actually spent hours and hours and hours doing this manually, and this matches my results pretty clearly. But the fact that it did it automatically was actually pretty impressive. So anyway, its conclusion is there is a 24-hour period there. So in conclusion here for this talk, as far as my proof of concept goes, if I use medium gain on there, I got results which were a little indeterminate, but were promising. So what I'm going to do is I'm going to continue to take more data, do more data processing, and be able to prove that more. As far as the ChatGPT goes, it's a helpful tool, but use it wisely. So just like anything else on the internet, don't just believe everything you say, but it's a good starting point. So that's my presentation, and good luck in your adventures. If anyone has any questions, feel free to reach out to me. My email, I believe, is included with this presentation. So feel free to reach out to me and I'll be willing to help you however I can. So thank you very much.